Assalamualaikum and a very good day. This is the module for material balance calculations for a single unit process. In this module, you'll be guided on how to extract out information from a given process description, draw a block diagram, label the known and unknown variables, calculate the degree of freedom of the process, and decide whether the process is solvable or not. Before performing the material balance calculation, it is very important for you to actually review the problem. By reviewing the problem, you can actually identify the process unit used based on the given keywords. For example, if it is mix, then your process unit will be mixer. If it is separate, then your process unit can be a distillation column. If it is an absorb, then it can be an absorption column. Or if it is to react, then your process unit will be a reactor. It is also very important for you to actually identify how many streams as per described in the problem. You can identify how many inlet and outlet streams as well as the variables or the composition or the chemical species that actually present in the process. Let us try this one. You're given a process in which benzene is mixed with toluene in a mixer. The benzene is fed at a rate of 3 kg per minute and the toluene is added at a rate of 1 kg per minute. You are required to calculate the overall flow rate of the mixture and to calculate the composition of benzene and toluene in the mixture. Let us see. Our keywords here are mixer, benzene, and toluene. Underline all those keywords. Before proceed with the material balance calculation, the first thing that we have to do is draw the flow chart. A mixer must have at least 2 inlet streams and at least 1 outlet stream. In general, we can draw a block diagram for a mixer as shown in this figure. Next, recall that a mixer has 2 inlets and 1 outlet streams. What are we going to do next is label the known streams or variables from the described process description and put it into the block diagram. Here, benzene is flowing in through stream number 1 at 3 kg per minute. Toluene is flowing in at 1 kg per minute in stream number 2. For stream number 3, we have yet to identify the values. Next, we are going to replace the variables on the stream and label the unknown streams. For stream number 3, we are going to denote the outlet stream as m dot for the flow rates. And since the compositions are interdependent, so we can choose one variable as x and the composition of the other as 1 minus x. Here we are going to have x kilogram of benzene per kilogram of mixture and respectively 1 minus x kilogram of toluene per kilogram of mixture. Once we label all the unknown variables, let us revisit the problem statement. We were required to determine the m dot, which is the total flow rate of the mixture in stream number 3. And we have to calculate the composition of all compounds in the mixture. Remember that mass fraction is an interdependent relationship, which means if we are able to find a value for one component, then we will be able to find a value for other components in the mixture. So, if we have x kilogram of benzene per kilogram of mixture, then the mass fraction of toluene will be 1 minus x kilogram of toluene per kilogram of mixture. Let us also check all the units involved in the calculation. Flow rate should has a unit of kilogram per minute, and mass fraction has a unit of kilogram of compound per kilogram of mixture. For non-reacting processes, the material balance takes the form of input is equals to output. The maximum number of independent equations that can be derived by writing balances on a non-reactive system equals the number of chemical species in the input and output stream. We should write balances first that involve the fewest unknown variables to reduce complex. So now, let us set up the overall equation for the process. Remember, input is equals to output for a non-reactive process. So our input are stream number 1 and stream number 2, and our output is stream number 3. Replace the terms with the known and unknown variables set previously. So we have 3 kilogram per minute of benzene added with 1 kilogram per minute of toluene is equal to m dot kilogram per minute of mixture. Next, we are setting up the equations for each component. Since we have only 2 components, we are going to set up only 2 equations for the components. We will go first with benzene. The inlet stream is 3 kg of benzene per minute. The outlet stream should have similar mass flow rate of benzene. So we have unknown, which are m dot of the total mixture, and x is the mass fraction of benzene in the mixture. Cancel out the units, we will be getting similar final units in kilogram of benzene per minute. Here we have 2 unknowns, which are m dot and x. Similar equations as what you had set for benzene can also be set up for toluene. You're going to take into account how much toluene goes into the system and make that equal to those in going out from the system. Next is to check the number of degree of freedom for the process. For this particular analysis, what you have to list out is the number of unknown. In our case, it is m dot and x. Number of independent equation, which is equals to the number of chemical species that's actually present in the system. So to calculate the number of degree of freedom, it is just number of unknown minus number of independent equation. So for our case, it's 2 number of unknown, 2 types of chemical species. So the number of DOF is equals to 0. It shows that the problem is solvable. If number of DOF is not equal to 0, then you have to recheck your flow chart or any other labeling of your variables. The last bit will be solving the problem. Recall our equation 1 on the overall balance. Putting in all the values, we are able to solve m dot to be equals to 4.0 kilogram per minute. Then we are going to plug in the value for m dot into equation 2, and by manipulating the algebra, then we are going to get x equals to 0.75 kilogram of benzene per kilogram of mixture. This ends this module. Please refer to the module 2 for the next section.